Okay, this is Green Architectural Engineering, part 2 of a lecture we've already started. If we look at the course syllabus, we're in here. My name is Joseph Wunderlich, Professor of Engineering, Architecture, and Computer Science. And we're down here in passive cooling and shading. And I presented PowerPoint last time and recorded it and then saved that as an MP4. Some of these you'll see like PPTX with audio. I record those offline and then play them as a PP4, but I believe that one, yeah, you did have to listen to that one. Students had to listen to that by themselves because I was in a meeting. All right, part 1's already online. Part 2 is just a link for when I'm going to put the next one online. It's recording right now, and that'll be right here. So let's go in and do it. Open it. Waiting for PowerPoint. Okay, so this is part 1. Let me get my Zoom controls out of the way here. I run the risk of not finding them again. Hide floating meeting controls. Okay, so I'm not going to go over all this again. We did this last time, but this is part 1. So we're looking at shading and passive cooling from our text, and they're combined together. So we did all this before. We looked at all this, and we looked at this, and there's different shading and Western and civilization, Eastern civilization, Frank Lloyd Wright passive solar things, stuff that I'm doing, writing a book on that, lecture series on that, some other Japanese related architecture, one personal note of where one thing that personal experience in one of those places. And then we looked into passive solar concepts, and then skylights and the light, how it's coming in, and the orientation of the building, as well as diffuse light coming in and reflected light coming in. Then shading methods, we looked at some of those, and designing overhangs here. And then type of overhang, but it's a little different. The arbors and awnings and window shades and louvers and blinds and glazing treatments. This project you see behind me is this one here, where I ordered $1,200,000 worth of Ford blue glass. I was happy to do it because I actually had to end up buying $1 million of steel. And actually, well, in today's dollars, it'd be over $2 million of steel from Japan because there was this pending strike in Pittsburgh. And, I was from Pennsylvania. I really didn't like having to do that. But so critical path with liquidated damages I put in the contract for contract to get done. We had to get the computer company in and all that. Anyway, trellises, plants, visits to Italy, roofs, balancing control. So this is where we ended and where we're going to start the next part 2, and talking about a balance between the thermodynamic characteristics of a building and the daylighting. So you may want the sun to come in for natural daylighting, but if you're in the middle of the desert, you could be overheating the building. So, there's a balance there. And then in the wintertime, you want the sun for both heating and daylighting potentially. Although there's other times where if you're on the northern face of your building, or if you're in a studio, architectural studio, an art studio, you typically don't want to be where the optimal sun fenestration is. The northern side is optimal for an elevation of glazing and windows for a studio because you don't have glare, but then you're dealing with the northern winds and the cold side and the lack of thermodynamic effects of the sun heating you up in the winter. So there's a balance, it's all balance. So this is where is new for this this lecture. And so part 1 was the shading part of combining these chapters of the book. And so this is passive cooling, which is certainly related. So cooling with ventilation and things we've talked about in other places too, tall ceilings, large windows, porches, space under building. And talked about that. We'll look at some of that built into the dirt kind of structures. Large attic vents, Japanese movable wall panels, see that more in the Frank Lloyd Wright lectures that I do. but it's also in the Ngawa that you watched the video of. Roby House floor plan. We don't have pictures of that here, but you can Google that sometime. You'll see quite a bit of window space and natural daylighting coming in there. Shutters with adjustable louvers. This is all different ways of cooling with ventilation. And now there's also health effects to this too, which we talked in other chapters. And the airborne viruses, aerosol form. So natural ventilation. A roof belvedere. Some of this, I mentioned it here without looking at it, but we're going to have a picture of that in a second. What that is, you see them on top of barns. It's a way of getting air moving through. It's a stack effect with the convection moving up and the thermodynamics of that, and we'll see that as well as the fluid aerodynamics effects of that, and the ventilation effect. So note, air obeys mostly fluid mechanics principles. However, it is compressible. So most of you engineers have taken some fluid mechanics, and you know that water's not compressible, but air is. So really, the main difference between all the properties and the Venturi effect and Bernoulli effect and all that you deal with fluid mechanics is just the air is compressible. Otherwise, it moves just like a fluid, obeying fluid mechanics. You typically analyze laminar flow because turbulence is too hard to model, and all the equations are based on laminar flow. But anyway, humans are comforted by evaporative cooling caused by air blowing on your skin, removing the moisture and heat from your body. So you see now for air, the velocity in miles per hour, the equivalent temperature reduction. And we had looked at this a little bit, I believe, when we were looking at the site design, and it was in there because we were looking at the psychometric charts and the adjustment of the comfort zone, that whole chapter on comfort we had, and moving that little box of comfort, in the region on the psychometric chart bound by there's entropy lines and humidity lines and dry bulb temperature lines. There's a little box that's ideal for comfort. And you move that box, that range of values for all those variables based on certain things. So if the air is blowing, that can make a difference too. So we talked about that. So you can reference that if you like. It's the same kind of thing as here. Stagnant's not good. That's one thing I noticed living out west for almost 10 years was not so much in Texas. Wind really blows sometimes there, but certainly in Southern California. Not so much in Northern California, but Southern California is beautiful, but sometimes the air just sits stagnant, except when there's Santa Anas, and you get like 80-mile-an-hour winds and the desert firestorms. It's a whole other story. So, so we're talking about passive cooling now, and make use of this. Do you have winds where you're at? Can you make use of them for cooling, right? For cooling. So the presumption is you're hot here and you want to cool yourself off. So the physics of air movement, we're going to look at some things of fluid or airflow and some basic principles. Flow of the wind is caused by a pressure gradient, a pressure differential. So if you look on weather maps and you see a giant pressure drop, there's usually a lot of weather associated with that when frontal systems come in, weather fronts. And then you create convection currents, right? So you may remember the three main parts of principles or aspects of heat transfer, of radiation, convection, and conduction. And you have a whole chapter on conduction when we talk about the thermal envelope, but we've talked about it in chapter 3, also. And then radiation we've talked about. But convective currents is a function of the temperature change, delta T. And then you have laminar flow and turbulent flow. You have eddies. And then you have separated, independent streams. So not, just concurrent to each other, but not, correlated necessarily. And then around shapes. So you see here now the positive, these are air pressures, positive and negative, and you want to think about that in the shape of your building. So if any of you have been to Minneapolis, it gets so cold there. Now the latitude's not much different than where we are in Pennsylvania, but because the jet stream dips down so much, you'll get 40 below zero there with winds and not a lot of trees. And so people build their buildings actually into the ground and really low because they end up sucking the heat right out of the building otherwise. And so you want to think about the profile of your building and how it would be in an air tunnel and a wind tunnel. Um, think a little bit about that when you're talking, because we're talking about uh, cooling now, natural cooling with wind. So these are roof slopes, pitches, right? And then, so this is, elevation views or section views. This are building footprint views. And you see there's some optimal shapes here: best, okay, worst, because the way the positive and negative is affecting what you're doing and whether you have eddies. Now, some of these can be nice. I live on top of a very windy hill, and so the northern winds actually come this way, and we're actually, my son Joseph just cleared a whole area and pressure washed this part of the building. We're going to build a deck out here, and there's a big piano in here, maybe put French doors and stuff like that. But it's blocked from the cold winds with nice views this way. And so, you want like a little eddy. You don't want the blast of winds. Now the prevailing winds are from the other direction here, but nevertheless, there's an eddy there that you can make use of. You maybe don't want the wind on you. Now we're talking about cooling here, so I shouldn't be mentioning the cold winds. But also, flow equals a function of adjacent buildings, terrains. This is a big deal in cities. If you've ever walked through Philadelphia in the wintertime, some of the narrowest streets. Helped my uncle in high school renovate a Chinese restaurant on Sansom Street. It's a real narrow street between what is it? It's near South Chestnut, and I don't know. Maybe one of you lives in Philly. Donato, you probably know right where Sampson Street is, right between two main streets. But it's a narrow street, and the wind would just blow right through there. Also in Chicago, wow, the wind there is even not near the city, and you get the tall buildings. Um, so the adjacent buildings can really accelerate what's going on, and the wind flow, airflow, the terrain, the same way, prevailing wind direction, and weather anomalies. So you'll see in California, because of the drastic relief change in the topography, growing right up to high elevation, the coastal range goes up to 2,000 feet within, a couple miles of the ocean, and you have a really cold ocean. And so you get these currents, these microclimates where the air is just like blowing down. I've seen actually the fog roll in because the thermals inland are heating up and dragging the air across the cold ocean. And the fog, June gloom, you have this thick fog comes in. And if you're driving the coastal highway up California, like from San Diego to San Francisco, anywhere where there's cliffs, you could see the fog like coming, looks like 100 miles an hour over top of you as it comes off the ocean up over the coastal range. So that's certainly cool you off more than you want. Actually, in San Diego, I lived in La Jolla on the beach. I had a beach place, and it was cold in June for 3 weeks because of the weather, the fog coming off the cold ocean. Anyway, basic principles: Bernoulli, Venturi. So most engineers have seen this before. I used to see it in Physics 3, and I could give you a whole history of all that. But most engineers, you're going to see all of this stuff you would have had in Physics 3 um, in your fluid mechanics and thermodynamics and other courses too, like this one. So the velocity is a flow. If your flow is constricted, the Bernoulli effect is you're going to, velocity is going to go up. So you got a laminar flow going through here at a constant, steady rate on a pipe that's not narrow, and then you narrow it, you're going to accelerate velocity. Venturi effect is you can suck air in. So you can pull air into your building by virtue of flow through your building. You can pull it in other ways. So here's an example. This is actually the Belvedere. I probably should label it that way. I have that picture on another page. But if you have, like, here's a wind velocity profile, not linear, but sometimes it's curves like this, and depends where you are on the terrain and the local climate. But that can happen. You can get very rapidly increasing velocities as you get above the ground. And and here you see the air flowing and being pulled into the building by virtue of Venturi effect, and here too, actually sucked in through an eddy here because by virtue of the air going through this way, like this. And by the way, you really need to ventilate all of your attic spaces because you remember from thermodynamics and our dew point review that because of the humidity, but also the temperature change, there's a point where you'll condense moisture out of the air and it will rot. It will rot. It will first dampen your bat, loose fill and fiberglass bat insulation and reduce your R values, but then it also can lead to mold and to rot of your wood because you won't typically do pressure treated wood this far above the ground. So you do need to ventilate. Typically you put the little soffit vents and then a ridge vent, and this acts by code in a lot of places. So this is for cooling as well as other benefits that I just mentioned: health, mold removal, rot prevention. So types of cooling: night flush cooling. So you pre-cool building at night and let the cool air in, and thermal mass cools, and then the heat sinks during the day. And so what you're doing is you're using this drastic change in temperatures in the desert typically, and the dry air, the big range of temperatures, you heat up during the day and release that in with thermal mass, heat collection through thermal mass, sun directly incident on concrete or water, or however you want to store it, and then naturally, passively, and then it releases it during the nighttime. And then in a similar way, you can pre-cool the building at night because of radiational cooling and thin atmosphere in the desert, you go down to freezing even if it's 120 during the day in the desert. And so you use that to your advantage and you cool a thermal mass and then you release that during the day. So it's kind of the reverse of using it for heating, right? As it is, because we're talking about cooling now. And then radiant cooling, we have direct and indirect. And so you can use the roof structure cooled by the night sky and the concrete. Indirect, night sky cools a heat transfer fluid, then the building cooled with it. Best for hot, dry climates also. Again, using these big temperature differences from the night and day, and the fact that you want to take a cold night and cool your really hot day. You don't typically have that in the east here, where in Pennsylvania, if it's hot during the day, it's not going to be super cool at night because it's humid and the heat's retained in that humidity and that marine layer that sits on top of us in hotter climates and hotter months. Now, this is something you'll see very common in a little bit in Texas, but really in Arizona a lot. You'll see during the day, during the hot months in summer, just these misters in the street, outside of shops, and outdoor eating areas, because you want people to get cooled off. So you're misting them, and the direct way you put water put into the air as it enters the building, spray mist, air through fountain or waterfall. Waterfalls is not really nice, pretty way for acoustics too. Well, falling water, by the way, we'll see, I mean, not the place, but the falling of water, showers and waterfalls will mask all frequencies of sound. So it's a nice acoustical break or barrier to, trafficy areas or noisy areas. But this is adding humidity. Now, you may want to do that if you're super dry. So you typically won't see misting, except where I've seen it in Hawaii a couple places, but there it's not so dry, and there's really nice trade winds that all the sailing ships came in on that blow all the time, and so you don't have to worry about humidifying the air or getting evaporative cooling enhanced by misting the people. Indirect here in the bottom to get the temperature down without humidity by spraying water on the roof, so not on the people, but on the roof, and this is a standing seam metal kind of roof. I mentioned I've worked on a little bit in Texas, some where it looks in context with the vernacular of the architecture, plus it also works well with the thermodynamics. It can get dented up if you have a tornado approaching, a huge hailstorm, but it'd have to be pretty big size hail, which I've seen. I've seen softball size hail, which actually doesn't fall that hard, although I had golf ball size hail dent up one of my cars when a tornado was nearby in Texas. I actually almost drove into a tornado once. I saw this, what I thought was smoke rising above on the horizon, and I was curious, so I started driving towards it, and then I realized it wasn't smoke; it was a cloud that was spiraling down almost on top of me by the time I got there. So if you see what looks like smoke coming from you don't know where, and you're in the middle of Texas, don't go trying to find it, or it might find you and take you someplace. So here's that earth cooling that I mentioned. Now, when in really cold climates in Minnesota and northern Wisconsin, people do this for warmth to get away from the blowing winds to take the heat away from the house. But we're talking about cooling right now. So earth cooling, direct coupling. So you're using the earth to cool you off. And so we'll look, and when we get to HVAC, you'll see these groundwater loops and other things. Well, HVAC systems, we're actually using the fact that the temperature below the earth is maintained at a pretty constant temperature to help with your HVAC design and active system. We're talking about passive now, passive cooling, direct coupling, where you just simply up against the earth and it's helping with cooling. Now, you may want to insulate to keep the heat in, but there's a direct coupling from the earth to the foundation walls and slab. Slab on grade, this is common in the south when you're not or in the west, southwest, you don't have to build below the frost line for the foundation. So, in hot climates, you get cooling right through the slab, and there's quite a bit. We'll see when we get to our thermal envelope chapter, quite a bit goes through the slab. Or the basement in general. Earth sheltered buildings here. So this is not digging down into the earth, but into the side of the earth. Cold climate here. I have have this. So the sun is on this side, and the north's that way. So this is the kind of thing you do, way up north, or where the jet stream blocks or dips down and zaps you with cold. So block cold northern wind, keep heat in with insulation. A roof garden, I've seen, I know some of you talk about that. Donato, you have that in one of your designs, I believe. So now this green roof, certainly something you want to think about. Now there's structural properties and moisture protection, leak protection that you're going to need to worry about if you're going to do this kind of thing. A really heavy load, not just the dirt, but the moisture that's being trapped up here. Essentially putting a shallow swimming pool up there, plus the weight of the vegetation too. And then you have to also worry about the insects and all that can, you normally put like a termite shield and bug prevention, even rodent prevention when you're down low in a lot of places, but you now have the earth right on top of you. So you've added some problems, but I think in the net result probably could definitely be beneficial, especially if the future sees some nice kinds of subsidies and grants for environmental things, which is a definite possibility if you look at what's happening today as the votes are counted. It's going to be close. Can wet soil? You can wet the soil with sprinklers to increase heat transfer. Also use trees and shrubs to shade the soil, right? So this is certainly a way you can cool yourself. Can also cover with gravel white, shades the soil, allows evaporation from soil. Okay, but need extra structure, extra drainage. I can do in cold climates, but keep heat in. If you're going to do that, insulate at dirt. Earth and garden can add insulating value. So yeah, dig into the dirt to protect from the winds. I mean, we're talking about cooling here, so presumably you're doing this where it's super hot outside, and so you're doing it to cool. But you do this kind of thing in the cold climates too. But then you're going to have some adverse effects trying to keep the winter cold out. Number 5, so 4 was direct coupling. We're talking about cooling methods. 5 is indirect coupling. Air enters building through earth tubes. Right? Channel it. I've never seen anybody do that, but 6, combine conduction, convection, and radiation. So you do heat sinks to draw in the conduction, and that will help create convection and some radiation as it releases the heat. And so we're going to go back. Well, I mean, just want to go back, but Roman vaults, we talked about these things before. So different natural shapes you might want to use in your passive design, the barrel vaults and groin vaults, cloister vaults, and the different domes of different shapes you can use to your advantage. And we'll see in the Pantheon we're going to look at in a second where this is happening. So a couple more shapes here. Basically, the rotunda, round room under the dome, square base with squinches. Those are the little things in the corners if you're putting a round dome on a square room. And then square base and pendatives, curved transitions between the cube and the dome. I'm not going to quiz you on that stuff, but there's just some things that you want to think about. And then this is some pictures. I think my son took this one in Venice. And there he is there. I could live in Venice. Love Venice. Been there 4 times. It's not enough. Go back. And then Rome. I've only been to Rome once, but I definitely want to get back there. And we have a relationship with the Pantheon Institute in Rome, and would have been going there most likely this spring break coming up, but it's now it doesn't exist because of COVID. So, but anyway, the Pantheon built 2,000 years ago in Rome, and it was the largest dome for about 1,400 years until Brunelleschi's dome, which is something I talk about in other courses. Brunelleschi, and that's in Florence, Firenze, and they did. When they actually built the base of it before they knew a way to make the rest of the dome. And Brunelleschi came up with a way similar to an eggshell kind of structure. An egg is what he used to demonstrate to everybody they could do it, and then a spiral. Kind of brick layout to transfer the load, but that's something for other lectures to talk about. Talk about the Pantheon right now and cooling, passive cooling in the Pantheon. So it's modeled after a sphere. You could put a sphere inside this thing, inside this. There's a picture of it. Now there were big steps 10 feet lower here. There still are, but because of 2,000 years of dust, 2,000 years of dust made 10 feet of your elevation change in your surface of the Earth. And so it's kind of weird, but when you walk around Rome, you'll see them finding new Roman ruins when they're digging down to do something for a new building or some renovation. And then suddenly they'll see some Roman ruins and they'll the corner, quadrant it off or light it up. See it underneath the building. It's kind of odd, but it's kind of cool. So anyway, this is a sphere. It's got a big hole in the ceiling, a big sphere with a hole in the ceiling, a big front door, a big portico, and what's called an oculus on the ceiling. And those 2 things alone allow for both lighting and cooling. So here's a combination. 2,000 years ago, passive, no funny gadgetry that would have broken a million times by now, or got hacked or screwed up during wars or who knows what. Still works. I stood in there while it was raining, by the way. I didn't get wet. The rain turns into mist as it goes down through the dome, and then there's floor drains built in that were built. Now, I didn't research to see if they were put in 2,000 years ago. I just thought I was about that now. I didn't look that up, but it's possible. They had the sewer system in Rome more than 2,000 years ago, so it's very possible, very much possible that this, and it was storm sewer and a sanitary system for, going to the bathroom. So the oculus, circular hole lighting, only other light source is the big giant portico. It's a big giant doorway, but those 2 things lit it up plenty. It was a rainy, cloudy day when I was walking through there, and I could still see all the artwork and the people just from the oculus and the front door. And then I think I went back another day when it was really hot. I didn't really feel the full effect of the convective cooling. Now, I didn't go back when it was hot because I went there in late February in Rome, and it actually was a beautiful time to go because you look at the latitude of Rome; it's far enough south that it's a real nice place to be in February. Actually, I think I had to still wear a coat, but I slept with my window open, and I normally wouldn't do that. I get cold at night, but it's relatively dry. So anyway, the currents here, we have thick walls that are a heat sink. I could talk about the whole structure here. I talk about that in other courses and the aggregate they use and the coffers and the distribution of load and the compression ring and all that and how that works. The structure of it. But right now we're talking about thermodynamic effects and the fact that it's a pretty thick structure at the base here that's acting as a heat sink and absorbs heat during the hot, humid days, and it also creates convection currents in here that cools off and the heat goes up and out. And the curved surface is actually accelerated. So that's using some of the airflow characteristics. So we're not only using the pure thermodynamic effects, but the aerodynamic effects also that are secondarily resulting from the thermodynamic effects. And then the people is what you're talking about now, evaporative cooling. You get the nice cool breeze over yourself. Um, and the heat rises and goes out the oculus. So 21 foot thick. Yeah. It's 2,000 years ago. And if you ever listen to my lectures on skyscrapers and all that, until steel, we had to have super thick first, second, third floors just to carry the load of the upper floors, and you really couldn't go very high at all without doing something or at all, even if you did something like that, until you had steel and the way you distribute the load and the fact that the steel can carry quite a bit, considering its cross-sectional area. You don't need to widen the base, but this is 2,000 years ago, and it's carrying a very heavy dome, relatively light because of the aggregate and the way they made it, tapering and the coffers, but still really heavy. A little better picture here. I didn't take this one. So whoever took that one, it's a very nice one. The Pantheon Institute's actually back here to the left, the architecture thing. Well, they have studios. The studios are around the corner here, a big studio space and presentation area around the corner. And then the school, a couple floors. I sat in Italian classes, a choreography class, and then I listened to architectural studio presentations in the evening around the corner here. And then they have dorms about less than a mile away with really beautiful dorms near the Tiber River down, you go south of here. That's the Pantheon Institute, which hopefully, apologize to anybody's graduating and not being able to. Well, I can't go either. I was going to go this year. I'm going to get back there. I mean, hopefully you will too, or get there. And then finally here, the last slide of this lecture, and then I want to talk about the projects, is the seventh way of cooling, and it's dehumidifying by getting the moisture out. And you see these little tiny packets sometimes in food or in your pockets of suits or nice clothing that you buy just to keep them dry. And desiccant, so it's a drying agent, silica gel natural, zeolite. Not sure exactly what that is, but it's not an element, I don't believe. No, it's not. Activated alumina, calcium chloride. I'm just listening to the ingredients I think I found on the label. Still in development. No, I made that note several years ago. I'll probably check, but chemicals above give off heat as they work. They also saturate with humidity. So, there's, I've heard of people doing this kind of thing on camping, but I don't know much about this, and this is something that you could look into yourself. I've heard about people putting them in stairwells under the stairs, big giant like sacks of this stuff to help dehumidify the house and in climates where you want to do that. And it also works as an acoustical dampening. So people walking up and down the stairs, you can dampen a lot of frequencies of sound transmissions. We'll learn in a later lecture on acoustics by with different types of mass. And So this is just one thing you could do in addition to drying the space, dampen the acoustical negative effects of people walking up and down the steps. Okay, let's see. I think I'll keep this running, this video here. Well, it's better. I think I just end the video.